Sure.
Also, I find some of the questions are very vague, so that you don't know what really is expected as an answer.
You mean the explanation was not clear?
No, like, what do we need to do? What was the question? That is not always clear.
Okay. So we
You need to go to the website.
I mean, where actually, one second, I think I remember.
You have to install.
So today we
or how
are,
to
we are
start?
going to start with like vectors and matrices in NumPy. So
Yeah, I get it. But then what I did is I changed the scale so that it's not coming to the square when we split it in the form. So that's why I get that. I just changed the scale and you corrected.
I mean, if I install it in another computer now, it has or not?
I don't know. I don't know how it is set up. Can you just type Anaconda in the search bar?
While Jim is setting up, maybe I'll ask. Sir, can I ask a question? Did anyone have any difficulty with the homework?
Yeah.
A lot.
Yeah, a lot of difficulty, okay.
For me, at least for me, yes.
Okay, so for some people it was trivial, and some people it was very difficult indeed.
I don't think it was trivial for anyone.
It wasn't trivial for anyone, okay. But this is, as I said at the beginning, we're going to do a lot of this kind of intensive exercise sessions, just to bring you up the level for the next semester. Okay. So we're going to have that one session in programming, and I think Jim is going to do something quite different today. Yeah.
okay.
Yeah.
So we can start now with NumPy and understand it with the law. So actually we can extend your like for this exercise, I mean, for coming week, because we are not going to have for next week we are not going to teach here, so you are going to have another
Mission planning.
yeah
Is it mission planning?
action planning
Yes.
for coming week.
You haven't heard about this. So next week there's no space informatics, but this is going to be another block course.
That was in November.
It's a space project management.
Space project management, thank you.
But that's,
Yes.
it says 4/11. That's for November.
Yeah. It's in
This is November, is it?
November, yeah.
Oh,
There could be
okay.
something else.
Well, this is good that we're asking you, because we're told one thing, you're told another thing. And so I'll clarify which is incorrect.
So for coming week,
Yeah. It may well be readjusted because the instructors can change their data as well.
Oh, yeah, I see here we have space resources fundamentals.
Next week.
Yeah, it's
Okay.
not the management.
Yes.
No, just
This is the
on
15th.
Tuesday, next Tuesday afternoon. Yeah,
Okay,
Next
yeah.
Tuesday afternoon, there's someone coming from Madrid.
exactly.
He's going to do a one-day course, and then he's going to do the rest of it online. So that's why there's no space in the math next week.
Yeah, it's okay.
Because we will have it.
okay. Can we start now?
Yeah.
So do you have any problem with Anaconda, and so do you have the notebooks with you? I uploaded a zip file. You should unzip it. So did you check the Moodle?
Yes.
Yes, of course, we did homework like that.
Yeah.
No, I mean for today.
Today,
For today.
okay.
For
Yeah.
today?
You
No, I
should
didn't.
first you should like download it, and because everything is there. I mean for
Did you do it?
this week.
You will do it?
Lecture 3, course
Uniform. Download. This
Lecture 3.
one?
Lecture 3.
This one. Yes, the last one. That one. Yes. Oh, okay. And to open it.
Do you want us to extract the graphics as well?
Yeah, we need graphics folder. Linux graphic folder.
In the repository.
Yeah, in the repository.
And there's also a folder called Mac OS.
Mac?
Something.
No, we don't need it. I think we don't. Maybe when I compressed the file in my computer, it added this file too.
In which document are vectors and matrices?
So yeah, vectors and matrices in NumPy. Can I start? So NumPy is the core library for scientific computing in Python. In this lecture, so I'm going to just give some like examples how you can create like vectors and matrices and do some linear algebra operations like matrix products and summation and different. So actually, to create an array in Python, you can just like write. First, you need, of course, to import the NumPy library. We can import it using like import method, and we can assign like another short name like np. So I think you understand it. Okay. So if you just write like np.array, it will create.
Could you enlarge the font for the visually disabled view?
Okay.
Thanks, that's good.
We haven't been introduced yet.
Oh, no, maybe.
It may not be the best way to introduce you as a disabled person for that. This is our professor, Dr. Mark. He's not serious.
The formal complaints should go to me.
We should have money.
Not about the whole program.
Okay.
But if you want to share anything with me, I have ways to transfer it to the organizers of the whole Space Master.
So an array can have like ranks. Okay. So if you have a one rank array, it means like a sequence. It is just an ordered list in NumPy. So it is not a vector. Okay? So if you want to have a vector, you need to add one more bracket here. Okay, so I can write it maybe. So if you have something like this, this is a sequence. But if so this is a vector.
Is it a column vector?
Yeah. This is a row, so this is not a column vector.
Okay.
It's not a column vector, yes. And so this is rank 1, and this is rank 2. So for vector for vectors, you should create it using like 2 brackets. Okay. So if you want to have like a matrix, you can do it like just, so this is 1 row. If you have 2 rows, it becomes a matrix. So this is matrix. And the rank is again 2. So if you increase the rank, it becomes a tensor. So if you want a tensor, let's say T, you can do it like you need 3 brackets now. 3, yes. And we have some numbers. Yeah. So
You said this is a tensor. Huh?
this is like tensor, yeah, the generic.
I'm not.
I write. This is rank 3.
What does it mean? I've never heard of it.
So if you have matrix is something like this. So tensor is 3-dimensional. Okay. This is tensor.
Which is 3D matrix.
In fact, 3D matrix. Of course, tensor is like a more generic term. You can have like n-dimensional matrix in a tensor. But here I have rank 3. This is rank 3 tensor. You can add like more dimensions.
So if we have like a 4-dimensional tensor, do we have 4 brackets?
Yeah, exactly.
Okay, and then 5. So.
You can, yeah, increase. And you can learn the shape of your array by just, let's say, can I erase it?
Right. Just one thing. So when you're writing the last one, the tensor, when you're creating that, so when you start with the 3 braces, so until when is the first one? Until where are you trying to write the first one?
Yeah, you need to follow actually the same rule what we have here. So if you want, so
From what I understand in the second last step is like when you write 1, 2, 3, then you write 4, 5, 6. So 1, 2, 3, then 4, 5, 6, then the next row. But how will the tensor form?
we can try, you know, an example. Let's say you have a tensor something like this: 1, 2, 3, 4, and 5, 6, 7, 8. Okay, this is your tensor. Okay. So this is the first matrix, and I have the second matrix.
Yeah, I don't understand.
I'm going to write the numbers now. So 1, 2, 3, 4, 5, 6, 7, 8. You can add this dimension. If we have 4, you can add.
So if we had 4 dimensions, what would it be called then? Still a tensor? Or?
Yeah. If you have, when you have a tensor, it is n-dimensional, like how to say, n-dimensional matrix.
How many brackets is on the end of the state? Because in this state is 4 and this is...
Yeah, there's missing a wrong bracket at the right.
This is 4 on
This
this
is for
side and...
the first matrix,
Yeah.
and this is for the second matrix.
And the last is.
So... You have 4 on this side and the ends only...
No.
Okay.
Now it's wrong.
Okay.
This is correct, but you needed to add the round closing bracket of the function array.
Now you
And now you're missing on the left side the square bracket before the 1.
It's hard. Just write it wrong.
Yes.
So let's move on, so if you want to create like specific, like special matrices in Python, let's say you need like all 0 matrix. You can write like just np dot zeros and the shape of the matrix. Let's say if you want like 2 by 2, like this. Or if you want like all ones, just very simply write again shape. Yeah. And like a generic constant matrix, which is called here like full, just like write again shape and the number, let's say 7. So this creates all 7 matrices. So if you need like identity matrix, it is done by I method. So
Can I ask one question?
sure.
But this matrix 7, 7, 7, 7, all 3 commands create this matrix, or only the last one?
No, just this one. So this creates all 7 matrices.
Okay. And
If you write it like here, like 8, it's going to be 8.
8.
All 8.
Okay. And the first two commands, what do they do?
The first fills the matrix with zeros, and the second with only ones.
Yeah.
So you have 1, 1, 1, 1.
Okay.
So in the notebook, you have all of them actually.
Okay.
So this is 0, 0, 0. This is 1, 1, 1, 1. Okay.
Thank you.
So, so identity matrix is, let's say, 2 by 2 identity matrix, 1, 1, 0, 0. N times N identity matrix is given multiplied.
Should that be 0?
Yeah.
Yes.
Top.
0. In math, in NumPy it is created like you write I and the number, let's say it is N. Okay. And yeah, if you want like create a matrix with like all random numbers, you can write like, let's say, E is equal to NP dot random. And again, the shape of matrix. Say, if you want, you can create, of course, like not 2 by 2 by, let's say, 4 and 5. For example. It will create randomly using uniform probability distribution between 0 and 1. So, can we continue? Are you okay with me? So you can read this array indexing like choosing like specific elements on a matrix, on an array. You can do it by slicing or array indexing. So we can also determine the data types in the array. Let's say it can be like an integer number or a real number, like a floating number. Do you understand it? Okay. Let's do some.
What is 64 for integer?
Int 64, you mean?
Yes.
Here? So that means basically you have 64, I think, binary. So you can, you can create an integer number using like 0 and 1s. Do you know how to do it? Like, so this means that you have 64 0 and 1s, and you can use it.
Binary system.
Yeah, binary system.
Like together 0 and 1 symbols 64.
What is like x type is integer 64, and what does it mean exactly? It's a matrix, it's an array 1 and 2, and
No, it means So you can write a number in two bases, okay? I mean basis 2, actually. So this is not, this is out of scope of this actual lecture, actually. So I cannot go into these details here. Yeah, you can check it. So so if you know that you can write, let's say 3, like in 10 bases as 1 1 in 2 bases. Okay. So this is 64. I mean, you have a 64 numbers to create. Yeah, to create the integers. So if you have, yeah, this it basically means that the highest number you can create is something like this: 2 power of 64 minus 1. The integer. And when you have 2, it is like 2 power of 2. So here we have int 2, okay? So now you have so as I said, so I cannot go details about it now. So so if you want to do like summation in I mean summation of matrices, you can just like write, if you have x and y matrices, so just write np dot add this is summation.
Yeah, so this is the flow. Yeah.
I have one question back to the types. Does it matter what type of integer it is? I would say no.
Sorry?
About the d types. Does it matter in any way, except from the different distinction between floats and integers?
So when you increase, so if you have float, you can, it becomes like generic, like a real number. So it's the memory for this is much more that we need. But when we have just if you assign like int 64, it will allocate less memory. So you do not need allocate a lot of memory if you have only integers. But if you have float numbers, you need to define it there.
Okay.
So if you don't define, and if you try to do some operations that includes like floats, it will give you like errors.
Is the only difference between integers and floats that you can just, what do you say, have different bigger numbers for float variables? That's the only functional difference.
So when you have float numbers, so the memory that you need to allocate is much more. So let's say you only work with 0, 1, and 2. Okay, you only have these numbers. Okay, so you should define the data type. Let's say maybe int 8. Okay.
And it it mean that the floating will contain 8 signs? So like
No,
One
2
will-
power of 8. So as I said, we cannot spend a lot of time on this. So yeah,
I think it's not important for this lecture.
yeah, for this lecture, exactly.
it won't be contained in homework.
Yeah, because potom
No, that's
The
okay.
question is rather, is it important relevant for us?
I think it's bigger numbers.
It's more important that you know the next step. So these are numbers.
So if you need to take the difference of these two, of these two matrices, so are you okay with this? Okay, to add 2 matrices.
Yeah.
Okay. So this is difference.
We can just do normal summation and subtraction to it on the same matrices with the same.
I think it will work also like this.
Yeah.
Yeah, it will work like this. But if you want to use NumPy's subtraction, you should write it like this. This is from Python. Like.
Yeah.
What is the recommended way to do the NumPy version?
So the difference is the implementation, isn't it? So basically, the reason why we're going for NumPy is because all the stuff we're going to use later is in NumPy. And the reason why they use NumPy is because they just provide an interface, and underneath it's implemented in one of a number of ways, depending on what architecture you're going to run it on. So it can be implemented for CPUs, it can be implemented for GPUs.
Okay.
So it'll be useful in the HPC cluster in the following week. So this is why Cengiz is presenting NumPy rather than the primitive operator.
Okay, so for us it's
Yeah.
better to use NumPy.
NumPy is more, it's just an interface for something else.
Okay.
You don't need to worry about what's underneath. Yeah.
Let's say you want to do like element-wise product of 2 matrices. So if you run, so by element-wise I mean like let's say we have 2 matrices. Okay, so this means like element-wise product. Which means, let's say you have 1, 1, 1, 1, 2, 2, 3, 3. Say these are 2. Something like this. So this is element-wise product. It means like you just multiply 2, 1 and 2 for each element. So this is element-wise product.
So can the rest be homework?
Yeah, you can. You can do like matrix product at home. I assume that you know what is the matrix product from previous courses. I think the lecture 1 was about linear algebra matrix product. So I want to switch to derivatives now. if you don't have any questions. Okay, so derivatives. So, do you have any background or any information about derivatives?
No.
Okay. Who doesn't have?
Speak for myself.
Okay. Then let's remember it now. So, let's say you have a function, okay? You have a function, and you want to know how fast it increases. Okay? And but to know it in a specific point. Okay? So first we need to know what is a slope in a function. Let's say you want to know the slope from this point to this point. Okay? And let's say you have function fx, and this is x, and so this is your slope. Okay, for these two specific points, let's say it is x1 and x2. So here I have fx2 and fx1. So the slope is fx2 minus fx1 over x2 minus x1. So the derivative is if you approximate this point to this point actually. When this one, when x2 approaches to x1. The slope on a specific point. But here I have the slope when I have this difference, okay, from x1 to x2. So derivative is defined so definition of derivative is like f prime, which means derivative of function f is equal to limits when. So let's say that x2 is equal to x1 plus h. Okay. So now x2 minus x1 is equal to h. Okay. And I have fx1 plus h and fx1. So the derivative is when this h goes to 0, okay? And I want to know this ratio. So you can, so in your notebook you have FH here. Can you check your notebook? This must be FX.
Yes, in my book. So it's incorrect.
So, do you have any questions?
I've done this before, but I can't remember why limits as h goes to 0. Why is the derivative defined as the rate of change as h goes to 0, since it's an increase in this case, it's a positive gradient.
So you mean that if we go from here to here,
Yeah.
Yeah.
we can go from here to here. Actually, it doesn't matter. The ratio will be equal.
But why h?
The slope doesn't change actually if you go from here to here, because we will go from here to here too.
So we define the limit as
It doesn't matter.
the left, but why lim h to 0?
Infinity.
Yeah, yeah, it should infinity, right?
No, you want the
No.
difference to be smaller and smaller and smaller, so that you have
Difference
only
between
one
these
point.
2 points. H means the difference between these 2 points.
You want to
It
minimize.
should be one
So
point.
when it reaches to 0, it defines your slope in that point. So this is
So it means the smallest possible
yeah.
distance.
It's more,
It means that
it approaches to 0,
Okay.
and you know the slope at that point. That point. Okay. It is something. Are you okay with this?
Yeah, I think so.
So you may have seen, like we have some like alternate notations for derivative, like so it can be like df or dx. Yeah. This is also used like. We should also change this here.
Example 1.
You will see some like dfx here.
Yeah.
It should be like just fx. So let's have one example. So let's say you have function fx is equal to x squared plus 3. So I need to add, to increase this function by h to calculate what happens when I move like x plus to x plus h. So it is like squared plus 2hx plus apply slope formula, like h, which is equal to first step, second step, and in this third step, so in the first step I just find the limit when h goes to 0, so x. So we say that f prime x is equal to 2x. Okay? So you can check these derivation rules for specific functions, and there are also rules when you have like sum rule, when you have summation, like difference, product, quotient. So this is like a homework, you can check it at home. So also we have some functions that are not differentiable. When we have a discontinuous function, it is not differentiable where it is not continuous. So in this course, actually, we are more interested in continuous functions. So you have an example for non-differentiable functions. You can check it at home. This example 3. Actually, you can run this code.
We also have this problem for the homework.
Yeah.
Do you have that in mind?
With the figures, you mean?
With the figures, yes.
Yeah.
You need to update your anaconda. Yeah.
Try.
I think we downloaded recently, so
Yeah.
only last class. It should be the latest.
We put when we call like math,
That's fine.
instead of putting notebook, we're putting like words.
You need to add this matplotlib
But
notebook.
Yeah, but if you
Yeah,
put
we-
inline there instead of notebook,
No,
then
it's
it's
exactly
like
It works.
yeah, it's the normal.
Like this?
Yeah.
So I did
But I
the
prefer
exercise with this.
notebook. Actually, this is you can control now the figure. Actually, you can resize it, and yeah. I don't know why it is not working. So
Can we put both?
you have maybe. So I suggest us to also to download PyCharm, which is very nice. PyCharm. PyCharm. If you don't, this is very nice Python like editor. Yeah, I use it like something like this, pie chart. So when you write something, it has like IntelliSense support. Yeah. Okay, let's continue with partial derivatives.
But you changed something in the previous one. It was in the exercise 3. It was some changing because I didn't matplotlib inline. We need to
Inline. Inline instead of notebook.
inline.
Here, you can, you see it
Okay.
inline.
And then okay. Okay. Thank you.
Yeah.
Okay. So let's say you have multi-variable functions. Yeah. So when you have a multivariate function, you can keep some variables unchanged and only take the derivative for one variable, which is defined by like nabla f over, let's say you have the function f x1, x2, xn. So here I assume that you have n variables. And let's take ith variable and partial derivative is so I go so here xi plus h, I go h length, I mean, h. So I only change xi. Take the difference. So x1, x2, all the other variables are fixed. I only change xi. Let's have an example with two variables. We have like say f x1 x2 is equal to x1 squared plus 3 multiplied by x2 squared. And let's say I want to calculate the derivative with respect to x1. So I have it. Yeah, it becomes like x1 squared plus 2h x1 So you should change these to x1 plus 3. It shouldn't be x1 squared minus 3, not x1 squared plus 3, because the function is x1 squared plus 3. In example 4.
I don't know if everybody knows, this is like LaTeX. I don't know if everybody, when we have to edit it, so maybe we could just, maybe you can make a note and we can update the notes after class removal.
Kind of figure it out. It's kind of.
Just so we don't make mistakes.
So here, anyhow, so I will I will upload the new version. Yes. Okay, let's. So if you continue here to like manipulations, so you will find like so for if you keep x1 constant and can calculate the same partial derivative with respect to x2, you can check it at home. So now we know how to calculate the partial derivatives, and we want to, let's say we want to know the increase of so we want to know the vector of the increase in 2 dimensions. So this is done by gradient. So let me introduce it first. Gradients. So basically, actually, it is if you have like again f and n variable function, it is given by the vector nabla f, which is all partial derivatives with respect to all variables. Okay. So note that this is a vector valued function. So actually, if we have still so if you are in a specific point, let's say you are like x1 equal to a1, x2 equal to a2. So you are here, okay? And if you calculate the gradient, it will show you the vector, the direction we should travel in order to increase the value of f most rapidly. So I have a video for this, for visualization. I think the best is to show it, to understand it. Visualization or like video is the best way to understand it. But we have some music.
We have the variable y. And we have z, which is a function of both x and y.
So this is a three-dimension.
Suppose that we pick one value for x, and we keep x at this one value as we change the value for y. Each time we change y by a small amount, z also changes by a small amount. At each point, the change in z divided by the change in y is given by the slope of this line. Red indicates a negative slope. Let's now pick a different value for x and keep x at this new value. Again, at each point, the change in z divided by the change in y is given by the slope of this line. The change in z divided by the change in y is what we refer to as the partial derivative of z with respect to y. Every point on the graph has a value for the partial derivative of z with respect to y. Here, green indicates a positive value, and red indicates a negative value.
So here you see the function increases, okay, but here it decreases. These green shows where it increases and where the derivative is positive, and the other side, when it is red, it is negative. Yeah. So this is partial derivative.
Every point on the graph also has a value for the partial derivative of z with respect to x. In this case, the value for y is held constant, while the value for x changes.
So this is with respect to y, derivative with respect to y. So x.
Suppose we represent the slope of this line with an arrow.
Yeah. So this is the gradient.
The length and direction of the arrow indicates if the slope is positive or negative, and by how much. Every point has an arrow that represents the partial derivative of z with respect to x. Every point also has an arrow that represents the partial derivative of z.
Yeah. So if we have two variables like f, x1, x2, so I have this. Two different variables I have partial derivatives. So this is the vector, this is the gradient. This is the gradient vector.
D with respect to y. If we add these two arrows together as vectors, then we'll get a new arrow. Let's call this new arrow the gradient of the function z. This arrow always indicates the direction in which z is increasing by the largest amount. The length of this arrow indicates by how much z is increasing in this direction.
So can I have a question? So if we have, let's say, a function something like this, it's a two-dimensional function, like parabolic, elliptic parabolic, like this. Okay, so f, x1, x2, you have x2 here, x1. So what is the gradient here?
Zero.
Yeah, when you have a minimum or a maximum in a function, the gradient becomes a zero vector. So now I'm going to actually mention about this, like mathematical optimization or minimization and maximization of a function. But before switching here, I have this example, so you can check it at home. And you have this function x1. I keep the same function. In previous examples, I had this function. So here we calculate like gradient, and here we have the Python code. So you can check at home this how. So this is actually the gradients, the gradient vectors. It shows. So you see when around here it is zero. Okay. I don't know why. Okay. So, do you have any problem with understanding gradients? What gradients mean?
It's just very old.
Great.
Comes back.
So,
What is NAFLA in the code?
sorry.
In the last code, example 5. What is NAFLA F1? Below.
Nabla is gradient. So when you define the gradient, so nabla f means gradient of function f.
And it takes it itself, or we should give it to the Python.
You mean the function?
Yes.
So of course we need to define the function and so where you are going to plot, I mean the minimum of maximum. So here I have done it actually, but this is like an example, and you can check it at home. So if you have any problem understanding it, you can send me an email or message.
And is
If you anyone
How
actually.
do we get these numbers? Minus 10, 10 and 100.
So we have this function f
This function.
x1 x2. Okay.
There is some result there.
X2 squared. So I want to see between minus 10 up to 10, when I change x1 from minus 10 to up to 10, how this function looks like. Okay?
But
It is just my choice.
okay, so it means minus 10 it's from,
Yeah.
10 it's up, and 100 what?
100
many
means
points
you
in
divide
between?
1 by 100, yeah,
Okay.
between minus 10 and... You need to check what is lean space. It creates just numbers.
Is there any function in the Python that can calculate the derivatives by itself?
Yeah, we have symbolic methods that can calculate closed form, what we did, what we do here. Actually, this is closed form result, analytical result. So there is, I think, another library which does this, but we are not going to use any symbolic. This is called symbolic computation. Okay, it understands your equation. Okay, and gives you the result. But here we don't. In NumPy we don't assume that it understands the question, the equations and calculate the gradients or derivatives. They are just numbers. Okay. So let's say you have a function something like this. Okay. Okay, you have function like this, and you want to find where it is minimum. Okay. So it looks like it is here, somewhere here, minimum. And we have x star where it is minimum. So you know what minimum means.
Gradient equals 0.
Minimum means when it is the lowest, when it reaches the lowest value. You see here it's high, it decreases, and here it is the minimum. You see?
Yes. Yes.
So here we have, as you said, like gradient, or here we don't have gradient because we have one variable function. Here the derivative becomes 0. Okay? Yeah, we'll discuss it later. So, we have mathematical optimization. So we are given a multivariable function like f, which maps from A to R. Do you understand this? What does this mean? Here A is some set of real numbers. Do you understand this notation?
I don't remember.
I don't remember. No problem. So let's say you have a set, okay, A, so set A, and you have here the set real numbers, okay? So your function as input takes numbers from A, okay? Let's say some lowercase a, okay? So here A is a number from set A, okay? Do you see? So let's say A here is like numbers between 0 and 10, okay? But your function gives a result which is a number in real number set. Okay? So let's say fx is equal to like x squared plus 2, where x is only a number in A. Okay? So x can be between 0 and 10. Okay? Okay.
It came back.
So I remove this part. So what is solved is just like a point. This is a vector. I'm going to write it like this. So this is a vector x star. So x star is in A. And we want to find if we have, here we have minimization, okay? This is minimization. maximization, we have this condition. For all x and a. And this is represented by the minimum of fx. You have actually in the notebook the same things. So in case you have maximization, you have you need to find a vector of x which is greater than for all x. Which is something like this. This is maximization.
Is there a meaning of the notation star that we are putting? Why it is not just x? I mean,
So
that we
x
don't-
star means where, give me the x where this function is minimum
all maximum.
or maximum, yes, the critical point. Yeah, we will see later that here the derivative becomes like 0. Can I erase? Or we are still waiting? So do you have any question? So by the way, we can write any maximization problem as a minimization problem. Okay? If you take just the reverse of this, like negative, this becomes like minimum. Like mirroring. Okay. So I think we can have a break now. Like 20 minutes.
And how should we send homework?
Homework? You mean for first homework?
Yes, yes. How do we give it to you? Or we upload in Moodle?
You can upload, but we will have like 1 more week extension.
Oh,
I mean, next week you can do it next week. Sorry? Yeah, I changed it. Actually, it was tomorrow. The deadline was tomorrow, but I give you like 1 week more. And if you have any problems like understanding,
Yeah, this is in detail, but like, for example, I don't know how to get.
So the deadline is not tonight. So the deadline is not tonight.
meaning that I
No,
will
yeah.
push this and
1 week later,
Well, I
then
just
I
don't know
was so
how to
worried
do
into
it. I just don't know how to make
So
things
working.
out.
I was doing it right now because I thought I wouldn't have time.
yeah, I see.
But no, sorry. You see how this
Can you guys show me the questions?
this is the question, but
Yeah, so in the question I didn't mention about like trying with or
play around
Stevie,
with
right?
it. And then I don't know. You're just trying to decide. So it's trying to be fine.
Next time you
I did it again.
different facilities to store values and other values, something like this.
You have this, the line ends directly at the, right? Mine is 2, but my graph
So I have to do this
starts a
again.
little bit before this. You know what I mean?
If you're working at we have from the beginning to know to make sure you use the minimal amount
The main thing is
storage you want.
Okay, so actually we need to choose ourselves how much memory it uses, a bit like C.
Yes, exactly.
Because normally Python does it automatically and use always
It's
So it's more about choosing smaller numbers than
Yes, exactly, yes. Yeah, these two.
little feedback from the book that we submitted.
Be aware that